So earlier, we talked about car going around in a circular curve, right, around the bend on a flat road. But when German engineers were designing Autobahn is a superhighway system throughout Germany. It was built around 1930s, I guess. And when they designed these superhighway system throughout Germany, they made sure that they were able to negotiate turns without worrying about any kind of weather factor. So, for example, if they were going through a turn and the road was completely iced up or snowed or whatever, they didn't want to worry about that. So, in order to negotiate that turn without friction, what they need to do was they need to bank the turn. So they actually had to like sort of bank it. And when you bank the turn, like from NASCAR race, right? You do not need any friction between the tires and the road to negotiate that turn safely. So all the turns in autobahns, right, as well as like exit ramps, they're all banked, like a speed racetrack, and it's pretty interesting how the physics works out that way. So hopefully, once we go through this, you'll appreciate banked curves when you, especially going skiing in your Poconos, when you get off that 476 turnpike, the exit ramp is banked because there's pretty much a lot of snow up there. Well, you'll appreciate it a lot more once you go over this thing. So here we go. All right. For a car traveling with speed V, now we just know it as V, around the curve of radius R. So it could be just any R, any speed, right? Determine a formula for angle that which a road should be banked so that no friction is required to keep the car on the road. Well, this is not an inclined plane problem where we have to like tilt the axis, right? Notice the axis right here. It is still horizontal and vertical for your x and y respectively, which means you do not rotate the axis to your x prime and y prime on this banked curve. Okay, so this not don't treat this as an inclined plane. Okay, the obvious force this car possesses will be the Fg, right? The weight. The normal force, which is perpendicular to the bankment, right? This is actually a bigger value than my Fg. So this vertical component of my normal force is equal to my Fg. And the centripetal force that creates and the horizontal towards the center of the circle is my other component, horizontal component of my normal force. Okay? So we have to break this up into x and y components where the normal force here is the hypotenuse of my vertical and horizontal component of my normal force. Okay, so this is the longest, biggest magnitude, longest length. So if we were to take a look at the y direction, okay, if we were to take a look at the y direction, sum of all forces in y is equal to m a y, right? How many forces are there in the y direction? Well, there are two forces that have F normal cosine theta, because because this is the adjacent to my angle theta. And I can prove that this angle is congruent to this angle, okay, simply by using geometry. So if I were to extend this, right, if I were to extend this, we know that this angle has to be theta, and this is the vertical angle of theta. Therefore, boom, theta, theta. Okay. So here, Fn cosine theta is vertical and plus Fg. So these two forces, and I'm going to consider up direction positive in this case, okay? So here, if I were to set these two equal to each other and give directions, MAY, now this car is not going to be accelerating off the ramp, or it's not going to go through the ramp, right? It's not going to, basically it's going to stay fixed on the road, so my acceleration in the y direction is 0. And we said F normal cosine theta is positive, so we're going to keep that as positive. Fn cosine theta, which is the adjacent component, minus Fg. And we know Fg is equal to m times g. Okay? So 0 is equal to Fn cosine theta minus mg. So if we solve for F normal then is equal to, I'll bring this to the other side of the equal sign, it becomes positive, so mg, divide that by now cosine theta, and this is my F normal. It's mg over cosine theta. Now let's take a look at the x direction. In the x direction, right, sum of all forces in the x direction is equal to ma. Now since this is going in a circle like this, right, so it is actually going in a circular motion, okay? And how many forces are there in the x direction? There's only one force, which is that, okay? In y direction, there were two forces. In the x direction, there's only one force, which is the opposite component of my normal force, which is Fn sine theta. Now remember, this right here is the theta, so the opposite is the x, and adjacent is y, so it is switched, so be careful with that. So here I have Fn sine theta. Right? If I set them equal to each other, I have MAC is equal to, Fn is going in the same direction as my AC, so this is my AC direction, therefore that's my positive direction. So my Fn sine theta is also positive. Well, we know AC is equal to m times v squared over r is equal to Fn, we know it is mg over cosine theta, so we can substitute that Fn in here as mg over cosine theta times sine theta, right? Look what happens to my mass. My mass cancels out. Therefore, you don't have all these different speed limits for, tractor trailers go at this speed, or, sedans go at this speed, SUVs go at this speed, smart car for two, don't go, right? So it's mass independent. So this is going to be for every car or every vehicle, okay? So they want us to figure out what the angle has to be. So they want us to figure out theta, right? Well, to do that, if we were to utilize this v squared over r is equal to now g times sine over cosine becomes tangent. That means if I solve for theta, I divide both sides by g, right? Then it is v squared over rg is equal to tan theta. Therefore, my theta is equal to then tan inverse of v squared over rg. This is the embankment formula. Okay? So once you know that, then you can figure out what safe embankment should be for certain speed with radius r. Okay. So here's an example here. Let's say what is the angle for a curve of radius of 50? So they give us r. R is equal to 50 meters. And speed v is equal to 50 kilometers per hour. We cannot use this because we need to convert this into meters per second. Okay? So this is equal to, if you were to actually multiply 50 kilometers per hour times, right, in 1 kilometer, there are 1,000 meters, and in 1 hour, there are 3,600 seconds. So you're basically dividing that 50 by 3.6. All right? So if you work that out correctly, you get 13.9 meters per second as your V. So this is the one you got to use. Okay? So what should the angle of the embankment be for cars to safely negotiate that turn at 13.9 meters per second with the radius of 50 meters in a circular path? That is, theta is equal to then tan inverse of, right, v squared over rg. So we can say theta is equal to tan inverse of v squared, that's 13.9 squared, over r, which is 50 times 9.8. So that is tan inverse of, well, what is 13.9 squared? That is 193.21. Divide that by 50 times 9.8, and I got 490. So my theta is equal to tan inverse of 0.394. So my theta is equal to 21.5 degrees is the correct angle for this embankment. So as long as this, I guess, turn is embanked at 21.5 degrees, this whole road can be completely iced up. And as long as you are traveling at 13.9 miles per or meters per second, it will safely negotiate that turn without sliding off the road. All right. So here, let's say you were going faster than this recommended speed of 13.9 meters per second. What is the tendency of happening with this car? For those of you who watch like NASCAR race, when they go into that first turn, right, The first turn goes like this, and then they turn like that. But if they approach that turn a little too fast, the tendency of this car is to actually slide up the embankment, right? It will slide up the embankment and it would actually hit the wall. So which way must friction act, right? If it's going too fast. So here, let's say, if it's going too fast, right, the friction has to act down the embankment in order to prevent the car from sliding up the embankment. Okay, so the tendency for the car is going to be sliding up the embankment. So this is my Hummer. This is my Hummer. So if it's going too fast, it's going to want to slide up the embankment. It's going to want to go that direction, right? So the friction has to act down the embankment in order for this to not crash into the all right, onto the wall or the guardrail. Similarly, if it's going too slow, what's going to happen? This car is going to try to actually slide down the embankment towards the pit stop area, right? So you don't want to go too slow either, right? You want to go at the correct speed. So if it's going too slow, right, then it's going to want to go in this direction, right? Therefore, the friction has to act up the embankment in order to prevent it from sliding down the embankment. Okay? So that is what's going on. All right? So I'm going to give you worksheet that can actually help you understand this or check your understanding. And I will stop my lecture for today here. Okay, I think that's all we need to know. And then Friday, we'll have a nice, easy day. Okay, I'm going to give you some opportunity to catch up on all the grades that you're supposed to accomplish and finish up with all your uploads and all your other tests. So many people still haven't handed in stuff that you're supposed to hand in, so make sure you do that. So I'm going to give you some opportunity to do that. All right. So we'll stop the lecture here.